What if I told you that our entire modern world, your smartphone, the internet, the global economy, even artificial intelligence, it all runs on a single microscopic invention, an invention so impossibly small, billions of them can fit right on the tip of your finger. Today, we're diving into the one tiny switch that changed absolutely everything.
And yeah, that really is the big question, isn't it? How can something so tiny have such immense power? Well, it turns out if you want to understand our digital world, you first have to understand the elegant, brilliant physics of this one little device. To really get a sense of the scale we're talking about, let's just start with a number. In a single recent year, humanity made 2.9 times trillion of these tiny switches. Now that is a number so big, it's kind of hard to even wrap your head around. It's more than all the grains of sand on all the beaches of the entire planet. We're talking, of course, about the transistor. But to really appreciate why it was such a revolution, we got to go back in time, to a world before it even existed.
So, what was the problem the transistor solved? Well, before we had our sleek, solid-state electronics, the digital world was taking its very first clumsy steps. And it was running on something much, much clunkier, a whole lot hotter, and made of fragile glass.
Say hello to the vacuum tube. You can think of them like light bulbs that could also act as switches or amplifiers. The very first electronic computers, like the famous ENIAC, were these literal room-sized monsters precisely because they needed thousands and thousands of these things to work. They were fragile, they burned out all the time, and they kicked off a staggering amount of heat.
I mean, just look at the difference. It is night and day. On one hand, you've got these vacuum tubes, huge, power-hungry, and constantly failing. You couldn't build a smartphone with them. Heck, you could barely build a calculator that fit inside a building. It was so obvious the world desperately needed a better switch.
And that better switch? Well, it finally arrived in 1947, in a laboratory that would completely change the course of human history. This was the moment solid-state electronics were born.
So the story goes, at the legendary Bell Labs, 3 scientists created the first point-contact transistor, and they absolutely deserved the Nobel Prize they won for it. And this thing didn't stay in the lab for long. By 1954, you could actually go out and buy a pocket radio powered by this new marvel. But the real game changer, the idea that set us on the path to today, came in 1958, putting multiple transistors onto a single piece of silicon. This created the integrated circuit, the direct ancestor of every computer chip that exists today.
So what was the magic ingredient here? Well, it all comes down to this special class of materials called semiconductors, and the most famous one of them all is silicon. Now, a semiconductor is amazing because it's not a great conductor like copper, and it's not a great insulator like rubber. Its real magic, its true power, is that you can precisely control its conductivity. You can literally tell it when to let electricity flow and when to stop it.
So, how do we control it? Through this incredibly clever process called doping. For what's known as N-type, we add some impurities that give the silicon extra free-moving electrons. Think of it as adding more players to a team, just kind of waiting around. For P-type, we do the opposite. We add impurities that create holes, which are basically just empty spots ready and waiting for an electron to jump into. This super simple process creates these distinct regions of negative and positive charge, and that right there is the absolute key to making the whole thing work. Okay, so we've got our special material, but how do we actually arrange these different layers of silicon to create the most important switch in the world? Let's take a closer look. All right, let's zoom in on the undisputed king of all transistors, the MOSFET. This is the guy that powers pretty much every modern computer chip. And its job sounds simple, to be a nearly perfect digital switch that can be flipped on or off with just a tiny bit of electricity.
The easiest way to think about this whole thing is like a water faucet. You have the source, which is where the water, or in our case, the electrons, comes from. You've got the drain, which is where the electrons are trying to go, and then most importantly, you have the gate. That's the handle. That's what decides if the flow is on or if it's off.
So here's where the magic really happens. When the gate is off, there's no path. The faucet is closed. Simple. But when you apply just a tiny positive voltage to that gate, something incredible happens. It creates an electric field that literally pulls electrons up and forms this temporary conductive bridge, they call it a channel, between the source and the drain. And just like that, the faucet is open and electrons rush across. The switch is on. Take away that voltage, the channel disappears. The switch is off. It is really that straightforward. On, off. And that simple on-off action, When you repeat it billions of times per second across billions of transistors, that is what built our entire digital empire. So let's zoom back out and see the absolutely mind-blowing result.
For over 50 years, the incredible growth of this empire was basically guided by this one famous observation known as Moore's Law. Now, this wasn't some law of physics or anything. It was more of an economic and engineering prediction, that brilliant engineers would just consistently find a way to cram twice as many transistors onto a chip every couple of years, making them faster and cheaper at a truly exponential rate.
And just look at the result of that prediction. It's wild. Back in 1971, a groundbreaking Intel chip had about 2,000 transistors. By 2006, that number jumped to almost 300 million. And today, a single high-end chip can have over 50 billion. The curve has just gone almost vertical. This relentless drive to make things smaller is exactly why the phone in your pocket is more powerful than a room-sized supercomputer from just a few decades ago. So what in the world are all these billions of switches actually doing? Well, they're arranged into these tiny little structures called logic gates, and they perform incredibly basic calculations like and, or, and not. But here's the amazing part. Every single thing you do on a computer, from the simple act of moving your mouse to watching this explainer right now to running a complex AI, it all just boils down to billions of these simple on-off switches flipping at unimaginable speeds to perform trillions of calculations every single second.
So we went from a clunky, hot glass tube to a microscopic solid-state switch. The transistor literally created our modern world. But Moore's Law, that engine of progress, is finally slowing down. We're now making these switches so impossibly tiny that the weird, strange laws of quantum physics are starting to interfere. And that leaves us with the great engineering challenge of our time. After an incredible 75-year run, what comes next? What's going to be the switch that powers the next revolution?